Section 14.3, Kinetic Theory of Gases. So as we move into kinetic theory, we're going to shift our focus to the smaller scale, right? Up to this point, we've talked about the macroscopic properties of gas, how much pressure, volume, temperature the gas overall has. Now we're going to talk about the individual micro properties, right, that comes from the motion of the particles themselves and how those micro properties can actually lead to things like the overall pressure of the gas. So it turns out the gas molecules or particles are in constant random motion, flying all over the place. If you contain them in a box, they're colliding with each other, colliding with the walls of the container, and each time they collide, that's going to change the particle's speed. It's still an elastic collision, right? But it's going to affect it, right? The other one might suddenly gain a ton of speed while the one is moving much more slowly now. So as a result, the atoms and molecules all have different speeds, right? It's this random smattering. So this changing speed, it turns out they're going to fall into a distribution of, depending on the temperature, we can know something about what range of speeds we expect to see for these gas molecules. Let's take a look at a graph that shows this idea. So this is the distribution of molecular speeds. Still imagine those gas molecules flying around and how they all have different speeds. What we have plotted here is the percentage of molecules per unit speed interval. So the percentage of molecules traveling at a certain speed, and then on the horizontal scale, we have the molecular speed itself. So for the blue curve, we have that the highest percentage of the molecules are moving at this speed near 400 meters per second. That's known as the most probable speed. That's just because it has slightly higher percentage of molecules moving at that speed than any other. The RMS speed, which is something we're going to see more of, is slightly higher than the most probable at 484 meters per second. That's another way of describing, it's sort of a way of describing the average speed of all the particles. It's similar to that idea. All right, so we notice this blue curve is labeled 300 Kelvin, and it says that when the temperature is 300 Kelvin, room temperature, the gas molecules can have a range of speeds from being basically zero, not moving, to 400 meters per second, all the way up to just over 1,000 meters per second, right? We notice there aren't a lot that are going that fast at room temperature, but there are a few. Most of them are in this comfortable range around 400 meters per second. What happens when we start to heat the gas up? Well, if we increase the temperature of the gas to 1200 Kelvin, significantly hotter, we find that the distribution of speeds increases, right? Overall, it shifts to higher speeds, that the most probable speed is now twice as much at 800 meters per second, and the RMS speed at this temperature is 967 meters per second. So increase the temperature, things start to move faster. But it also flattens out the curve where there's a lot more that are going way, way faster and still some that are going slower, right? You can still find a couple that are barely moving compared to all the other gas molecules. So we see that the temperature here, as there's a higher temperature, we see more variation in the speeds. The gas molecules are more chaotic. A lot of them are moving faster, but some of them are still moving slowly. As we imagine all of these flying around, these gas molecules are exerting a force on their surroundings. So we're going to imagine putting the molecules now inside of a box. This is known as kinetic theory, and we'll imagine just one gas molecule to start, and to help us imagine it, we'll pretend it's a ball. And if you throw a ball against a wall, it exerts a force on the wall, right? It's similar to a gas particle, right? But the gas particle is going to have a much a smaller mass at a much higher speed, unless you can throw a ball 400 meters per second, in which case, what are you doing here? You should be in the major leagues. No, you'd be causing problems in the major leagues. Anyways, gas molecules way faster than a ball, even though they're tiny. But you can imagine, as you throw it, that exerts a force on the wall. And we know force is related to pressure, right? We saw previously that our pressure is equal to the force divided by the area. So if we know the area of the wall and we know how many collisions are exerting a force on it, that can give us our pressure then. We can also figure out, see what we can do to figure out the force using none other than Newton's second law, right? It pops up yet again that the sum of the forces is equal to the mass times the acceleration. Here we're going to focus on this one collision, the ball or particle with the wall. And so it starts out with a positive velocity, it hits the wall, bounces off, elastic collision. So it has the same speed, the opposite direction. It's now negative velocity. So the acceleration will just be the change in velocity over time. And we know that we can write this mass times change in velocity. That's looking like our momentum. So it turns out the average force the particles exert on the wall can be given by final momentum minus initial momentum, divided by the time between each of these collisions. So our final momentum is the mass times the negative velocity, negative mv, minus our initial momentum, positive mass times velocity. So we end up with negative mv squared because we have an extra velocity down here. This has to do with the time between the collisions, that if you look at one particle traveling through the box, it has to travel the length 2L before it reaches that distance again, right? So that is our distance, x is 2L. And we know that position, velocity, and time are all related, right? That velocity is equal to the change in position over the change in time. So what we've done here is to solve for that time, the delta t, we've swapped the delta t and the v. So delta t is equal to delta x all over the velocity. And our delta x again is 2L. And that's what's been filled in here. So the velocity goes up to the top. The 2 cancels out with the 2 that we get from the momentum. And so this gives us the average force that's exerted on said wall, the force that a single particle would exert on the wall. All right, we can take this further. So let's keep exploring. So the single molecule, the average force is mv squared divided by the length, which is just the size of our box. If we have n molecules in 3 dimensions instead of just a single dimension back and forth like Pong, then the average force is going to be this same average force, but times the n molecules, because we have n times as many collisions, divided by 3, because now they're colliding with the other walls too, right? We have 3 different dimensions to go between. So it divides out, we get a few less collisions with a single wall. All right, so going back to our pressure equation, we know that pressure is force over area, and the area of these walls, because it's a nice square, is just given by L times L, which is L squared. So if we fill that in and connect it with the force, we get that the pressure is equal to N divided by 3 times M times this V squared average, which is a way of saying, hey, we now don't know the exact speed of all the molecules. We did when it was a single molecule, but now we have a bunch. So we'll take an average of that V squared. And then in the bottom, we have L cubed. That's our volume, right? Length times width times height of a cube. That's just our volume V. Cool. So we are now starting to pick up steam. We're going to keep powering through. So we get that the pressure is equal to N over 3 times M v squared average divided by the volume. This v squared average, as I mentioned, is more specifically the root mean square speed, or known as VRMS squared. The way you can calculate it is by squaring all the individual speed velocities and then taking an average of them. So it's not the same as taking an average and then squaring it. You first have to square them before you take the average, and you get a slightly different value that way. All right, so from here on out, we're going to use this notation, VRMS, to refer to this. And if we continue on, multiplying our volume across to the other side, we get PV is equal to 1/3 N times M VRMS squared. Now this is looking pretty good. MV squared, we've seen that before. That almost looks like our kinetic energy. So to make it look fully like our kinetic energy, we're going to put a 1/2 there and pull out a 2 in front so that we're just multiplying by 1. We aren't actually changing anything. So 2/3 N times 1/2 M VRMS squared. That's just our kinetic energy, but it's going to be the average translational kinetic energy. So our average translational kinetic energy is 1/2 M VRMS squared. But the other side, PV, we know we can express in terms of this capital N as well, NKT. So we have NKT is equal to 2/3 times capital N times this kinetic energy average. And what you'll notice here is that the N's will cancel out. And if we solve for KE, we just have to multiply both sides by 3/2 to cancel out the 2/3 on the right, and we'll be left with 3/2 on the other side. And so we get that our average translational kinetic energy can be calculated with 3/2 K, the Boltzmann constant, times the temperature. This tells us that if you just know the temperature of the gas, you can know its average translational kinetic energy, which is pretty wild. Thinking about all the different gas molecules flying around, and all you have to do is know their temperature. With this in mind, let's think about a conceptual example. Does a single particle have a temperature? Each particle in a gas has kinetic energy. On the slide, we've established the relationship between the average kinetic energy per particle and the temperature of an ideal gas. Is it valid then to conclude that a single particle has a temperature? Yes or no? I want you to think about this before you move on, so go ahead and pause the video now. Right, hoping you did that. Well, let's think through a moment. If each particle had a temperature associated with its kinetic energy, because we saw that each particle has a whole range of possible speeds, right? So they all have their own kinetic energy that's very different from the others. If they each then have a temperature associated with that kinetic energy, then there'd be a huge range of temperatures within the gas. And that doesn't really match what we expect, what we observe even, right? If you stick a thermometer in a gas, it just gives you a single temperature. So gas, if it's at thermal equilibrium, which is a fair assumption, only has one temperature, and that's exactly what the thermometer spits out. So what we saw on the previous slide is just going to give you the average kinetic energy and how that connects to a temperature. It's not going to be the overall result of all the individual particles. So that's a key distinction there. With gases, we can't always talk about the individual particles. Sometimes we have to talk about the overall effects. All right. Let's see an example of the speed of molecules in air. This is cool. Air is primarily a mixture of nitrogen, N2 molecules, molecular mass 28U, and oxygen, O2 molecules, molecular mass 32U. Assume that each behaves as an ideal gas and determine the RMS speed of the nitrogen molecules when the temperature of the air is 293 Kelvin. How would the RMS speed of the oxygen molecules compare? All right. So first off, we notice we have the molecular mass of the nitrogen and the oxygen. We also know that they're behaving as an ideal gas, and we want to find the RMS speed. We want to find VRMS given this temperature, 293 Kelvin. Well, we know that the VRMS, 1/2 mVRMS squared, is equal to 3/2 kT, based on our kinetic energy equation. 1/2 mass times VRMS squared is equal to this 3/2 kT. So let's see, we know the temperature, we know the Boltzmann constant, we want to find VRMS. What about the mass? Well, notice we know the molecular mass, and so knowing the molecular mass, we can convert this into our standard mass units of kilograms. So with that in mind, let's give this a go. All right, so we note that we have 1/2 mVRMS squared is equal to 3/2 kT. That's the equation we just wrote there. And if we solve for VRMS, we get the square root of 3 kT over m. Note, this is a general formula. Because it was solved all with symbols and nothing specific to this problem, this is something you could add to your crib sheet. That's totally fair. All right, so then for nitrogen, we need to figure out the mass of it. So we could take the 28 grams per mole and divide by Avogadro's number, and that would then give us the number of grams, and we could then convert that to kilograms. The other approach we could take here that's equally valid is we could take that 28U and we could use the conversion factor we have between U and kilograms. So we saw that 1U is equal to 1.6605 times 10 to the minus 27 kilograms. And so the U's would cancel and we'd be left with kilograms as well as this number out in front, 4.65 times 10 to the negative 26. So whichever method you're more comfortable with, either one works, right? They're both entirely valid. Once you have that mass, then it's a simple plug and chug. We already rearranged the equation algebraically, so we can just plug in our 3 times our Boltzmann constant times the temperature divided by the mass, and we come out to 511 meters per second. That is so fast. That's blazing. Wow. Okay, so that's for nitrogen. What about for oxygen? Well, we remember nitrogen was the 28U and oxygen was 32. So what does that mean? That means our mass has increased. If our mass increases, mass, notice, is in the denominator. So if our denominators gain bigger, what's going to happen to our RMS speed? Our RMS speed is going to have to get less. It's only slightly less. You can do the calculation to check, but you should find it comes out to about 478 meters per second. So that covers you there. All right. One last thing in this section of the kinetic theory of gases. It also helps to be able to describe the internal energy of a gas. The internal energy is the sum of all the types of energies that it could have, right? For monatomic, ideal gases is the simplest case. We treat them as basically particles. And so the rotational inertia is negligible. We don't have to worry about the kinetic energy of the molecules rotating. We don't have to worry about vibrational kinetic energy because we don't have any chemical interactions or weird bonds between the molecules. We just have their collisions bouncing off each other. So the one kind of energy that a monatomic ideal gas has is kinetic energy. And the kinetic energy will just be however many molecules there are, n, times that kinetic energy. So this will give us our internal energy of a monatomic ideal gas, n times 3 halves kT. And we note that big N times K could also be written as the number of moles times the Rydberg constant temperature. So the U here, our internal energy, can be calculated just if you know the number of moles or molecules and the temperature of your gas. And this applies for a monatomic gas, but we'll see that any gas, the internal energy is going to be proportional to the temperature. As the temperature increases, we'll see the internal energy increases as well. So this is something that we will continue to see. It's going to come up again in chapter 15. So hold on to this idea. It is a good one.